Did I guess it? He's being a little.
All right. So if we want to talk about an exponential function, that's something of the form like a times b to the x. But we got a couple of requirements here. One of them is that a is non-zero. Another is that b has to be positive and not equal to 1. So let's think about why we need these requirements. Why does what would happen if we let a be 0? Then the whole thing is just 0. That's a constant. That's not an exponential. Okay. What if b is 0? Same thing. Whole thing is 0. So that's, that's not helpful. What if b is 1?
Then a is just going to be the answer.
Yeah, then it just is another constant. It's just going to be y equals a, since 1 to any power is still just 1. What would happen if b is negative? Why don't we let that happen?
If you have a negative number as a result to the x power,
So?
it wouldn't be exponential, it would be like this.
So?
It's just not how exponential functions work.
Okay. What else? It wouldn't necessarily even look like that, what you're describing. Because all you've done is you've thought about integer values of x. What other kinds of values could x have?
Oh, fractions.
Okay, specifically what kind of fractions would be a problem? No. Improper fractions could be fine.
Negative fraction?
No, not even negatives. No, partial fraction isn't a thing for like an actual fraction.
An imaginary fraction.
Okay.
A square root fraction.
Yeah, there you go. So what fraction is the same as a square root?
Square root of 1. Square root of 2.
No, but like what x fraction? So the variable's in the exponent, right?
Yeah.
What exponent is the same as a square root?
1/2.
1/2, right?
Yeah.
1/2. So any exponent that has an even denominator is the same thing as an even root, right? If you try to do that to a negative number, what's going to happen?
It becomes positive.
You get an imaginary result,
Oh.
right? Like if you try to square root a negative. So not only is this function going to be like bumping back and forth between positives and negatives, it's also going to have an infinite number of discontinuities all over the place. So it's going to be like infinitely discontinuous. And now this thing is starting to resemble nothing like any kind of function we want to deal with, right? Everybody okay with that? So just FYI, the exponent is the exponent. The a we call the initial amount, or sometimes we just call it a coefficient. B we call the base of the exponential. Worth mentioning, there's a key feature for all exponential functions of this type, that they have a horizontal asymptote at y equals 0. You can imagine as b gets infinitely small, so like negative infinity. As x gets infinitely small, you have like 1/b to the infinity, which is like 1 over like a trillion, which is basically heading towards 0, right? Let's look at just some quick examples to review our exponent rules. So let me drop in a set of those. Bloop. So let's say we have the function f of x equals -2 times 4 to the x. Can I write that as -8 to the x? No, why not? Okay. What are our rules for exponents when it comes to multiplying?
Before multiplying.
Okay.
You can't they have to have a like base.
Or they have to have a like exponent, right?
Yeah.
If I have two things with the same exponent, I can multiply their bases and keep the exponent. Or if I have things with the same base, I can keep the base and add the exponents. But what I have in our example has a different base and different exponents. There's nothing you can do simplification there on that. Everybody kind of cool with that? Okay. These exponent rules that we're talking about right now from Algebra 2 are some of the things that are the most common mistakes students make in terms of trying to simplify stuff. So if we did f of 2, that just means we're going to be plugging 2 in for x, right? Negative 2 times 4 squared. 4 squared is 16. Negative 2 times 16 is negative 32. Everybody cool there? F of 0 means we're going to have negative 2 times 4 to the 0. What's 4 to the 0 equal? 1, which is equal to, so negative 2 times 1 is just negative 2. Remember that anything non-zero to the 0 power is equal to 1. 0 to the 0 is?
0.
Nope.
1.
Nope.
It's negative undefined.
It's indeterminate, meaning that the value could be many things, not just one. So undefined usually means that the value would be infinite. Indeterminate means depending on the problem that you wrote, it could be 1, it could be 0, it could be infinity. We're not really sure if that's something. If you're taking AP Calculus next year, we talk about these situations, which is cool, right? Also worth pointing out, 1 to the infinity, also indeterminate, which is weird. Why isn't that just 1? It's not. Ooh.
Wait, why is it 1?
Well, that's a whole day's discussion about these indeterminate forms.
Can you say it quick? No, actually, it's a whole day discussion.
It's literally I need my notes. I can't just. It's complicated because the point is that you have to use limits and you have to kind of know about limits.
So I thought 1 to let's say 1 to the power of 5 is still 1, right?
Yes, 1 to the finite is 1.
Yeah.
1 to the infinite, indeterminate. That's the weird thing about these infinites. Infinity's weird. All right. Let's say we have negative 2 times 4 to the negative 3. What do we do with a negative exponent? Makes a reciprocal. 4 to the third is 64, so 1 over 64 times negative 2 is going to be negative 1 over 32. So I'm just kind of writing the exponent rule down on the side for us. Is that cool with everybody? All right. F of 1/2. What's 4 to the 1/2 the same as? Yeah, square root. So the square root of 4 is 2, so negative 2 times 2 is negative 4. So a to the m over n is the same thing as the nth root of a to the m. And then e, f of negative 3 over 2. How do I do 4 to the negative 3 halves without a calculator?
No.
So the way I would think about this is I would break it up into 3 different exponents, because negative 3 over 2 is the same thing as negative 1 times 3 times a half. Now I'm going to choose to do the 1/2 part first. Why would I choose that?
It's too easy.
Yeah, 4 to the 1/2 is easy. That's no calculator, no problem. So 4 to the 1/2 is 2, because that's the same thing as square root of 4. 2 2 cubed is
4,
8.
6, 8.
One of those. I'll get it. And then 8 to the negative 1 is 1 over 8. So negative 2 times 1 over 8 is negative 1/4. And again, what we did there is we used that the exponent of an exponent is the product of the exponents. So far, so good. No big deal, right? Just wanted to remind us about our exponent rules. Next example here, we're going to take some points and going to write the exponential function that represents those points. So it's asking for an exponential function. So that's going to be something that looks like y equals a times b to the x, right? Of these points in our table, which ones are going to be the ones that I'm going to be most interested in to do this? Any of them will work, but 2 of them are going to make life easy.
0, 1.
0, 3, and 1, 15. So if I use 0, 3, that's an x and a y, right? So I can plug in the x and y. B to the 0 is 1. How do I know b isn't 0, though? It's an exponential, so I know the b has to be greater than 0. So it can't be 0, so I'm fine saying that that's just 1. So I just get a is 3. From the other one, then, what can I do? I can say 15 is equal to my new value for a times b to the first. So b is just 5. So I have the equation y equals 3 times 5 to the x. Done. Mr. Kulik, pretty easy. Yeah, if you used any of the other points, you'll still get the same answer, but like the algebra is a lot stinkier. Which again, my life is stinky enough. I don't need to make my life stinkier than it needs to stink. But that being said, what happens if you don't have the option other than get stinky? You gotta go stinky here. So again, we have an exponential function. So we know that our answer needs to look like this, right? So what I'm going to do is I have 2 sets of x's and y's. So if I plug those in, I have 2 equations, each of them with 2 variables in it. That's going to form like a system of 2 equations. Last year, when you solve systems of equations, you probably use substitution or elimination rather frequently. In those cases last year, when you did elimination, the variables were being added or subtracting, right? Because you had like a polynomial looking thing. So to use elimination when the variables are being added or subtracted, you added or subtracted the equations together to cancel the variables. In this situation, since the variables are being multiplied, what are we going to have to do to eliminate the variables? Divide. Excellent. So the question is, which equation should I divide by which? Which one should be the numerator? Which one should be the denominator? What I always do is I take the one with the biggest exponent and divide it by the one with the smaller exponent. So negative 1 is bigger than negative 3, right? Because negative 3 is more negative. So we'll write that 12 over 48 is equal to a times b to the negative 3 over a times, negative 1 over a times b to the negative 3. 12 over 48 reduces to just 1/4. The a's cancel out. And then how do I do b to the negative 1 divided by b to the negative 3?
You make it b second.
Yeah, how'd you do that?
You bring the 3 out. You make it positive. You add it to negative 1.
Yeah, you subtract the exponents, right? So negative 1 minus a negative 3 is positive 2. So we'll square root both sides of that, and I get plus or minus 1/2 is my value for b. But remember, b is the base of an exponential, right? So I know b has to be greater than 0. So I can drop the minus. So I just have a half. And then I'm going to take that answer and plug it back into one of the equations. It doesn't matter which one. I'm going to pick the one with the more convenient exponent. That would be problem B. What's 1/2 to the negative 1?
2.
2. So to solve for a, I get 6. So I can say y equals 6 times 1/2 to the x. We cool there? Okay. One of the things that makes exponential functions potentially inconvenient is because it's difficult to compare two exponentials when they have different bases. So one of the things at some point in the future that we're going to want to try to do is to figure out a way to rewrite these exponential functions so that they have the same base. So one of the questions that we're going to have is, okay, what number should I use as that common base? Well, the canonical number that we use is the natural base, or something called Euler's number. So those two terms could be used interchangeably. And the symbol we abbreviate this number with is the letter E. The way we compute E is it's the limit as x approaches infinity of the sum of 1 plus 1 over x to the x. And that irrational number is approximately 271,828,1828, yada, yada, yada. Again, it's irrational, so there's no pattern. Goes on forever, never repeats, never stops, like pi. Now, later on, we'll talk about how where this kind of comes from, but initially what you would have done to evaluate this is you'd probably just do this numerically. So I just created a table of like x values, and I just created a whole bunch of them, 322 of them. And then I did 1 plus 1 over that x to the x and just computed that. Excel does this really easy. It's like a drag and drop thing. And as you see as I go on, just kind of like computing and getting closer and closer. And depending on how close you want to your actual answer, just depends on how many x's you have to go through. If you need 2 decimal places, what did we go through to get that? We did right here about 164 to get 2 decimal points. You'd have to do more to get more, but like Excel is good at this. Computers are good at this kind of recursive work. We'll show you how we do it in practice, how we could do this limit in practice, but we'll do it a little bit later on when it makes a little bit more sense. All right. So with this in mind, we might say that we have a new definition then for our exponential function. So we can also write as a times e to the kx. Again, we have some constraints, but there's less constraints, just that a can't be 0 and k can't be 0. Otherwise, we're good to go. Again, if you think about what's going to happen if a is 0, well, the same thing as before, you just get 0. If k is 0, then you have e to the 0, which is just 1, so constant. If k is negative, it's no problem because it's just going to make a reciprocal, right? It doesn't actually make the sign of the base negative. It just makes it a reciprocal, which is fine. Everybody cool? Okay. So oftentimes we want to classify these exponential functions kind of into 2 types. The first type is growth, And there's really kind of two types of growth. There's like unbounded growth, and then there's like bounded growth. So on an unbounded growth, as you move from like left to right, your exponential is growing without bound, right? There's nothing kind of capping it. Bounded exponential growth, you have something like this where you're growing as you go from left to right, but the asymptote's kind of keeping a cap on like how big that can get. So if we have our two different types of exponentials, we can identify whether we're talking about growth or decay just by looking at the values of our coefficients. So if we have unbounded, that's where a is greater than 0 and b is greater than 1. Or if it's the other form, we have a greater than 0 and k greater than 0. If it's bounded, we have a is negative, and then b has to be between 0 and 1. Or here we have a is negative and k is negative. The other type of exponential is we call these decays. And again, we can have bounded decay and we have unbounded decay. If it's bounded, it means that we're like kind of heading down to an asymptote. So that's like a minimum value. If we're unbounded, we're heading down still, but this time we're operating underneath the asymptote. So you can get kind of as low as you want. So bounded decay, that happens when the a is positive and the b is between 0 and 1. Or when a is positive and k is negative. And the unbounded kind happens in the other situation where a is negative and the b is positive, or I'm sorry, bigger than 1, or when the a is negative and the k is positive. Is everybody okay with that? So just some criteria to recognize like how you know what type you have just by looking at the equation, so you don't have to generate a graph or whatever. All right, let's do a story problem example of using one of these exponential situations to kind of answer a question. Okay. Given the population of a certain city in 1990 is 782,248 people, and the population of the same city is 200,895,193 people. Boy, I said that wrong. And assuming that the population growth is exponential, so we know that we're going to look something like this. In what year will the population reach 1 million people? Well, since we're said population here, I'm going to think about this as a function. So I'm going to do P of t and t. So part A is just going to be creating a model for the situation. And the second part of this then is going to be solving that model when it's equal to 1 million. Right? So to create that model, I'm going to be using this where t is our, where the year is our input and the population is our output. So I'm going to think about these as points. And now when I look at this, if I look at my x coordinates here, I notice that neither one of these are 0, right? Which makes it kind of inconvenient. It'll be very similar to example 3 that we just did. So instead what I'm going to do is I'm going to say, well, what if t is the years since 1990. If I do that, then that first point would turn into 0, 782,000, yada, yada, yada. And the next point would turn into 10, comma, 895,000, yada, 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 right? Why is that going to be helpful? Because it's going to give me my A value for free. And now I don't have a system to solve to find B, which is my preference for doing this. Everybody's cool with that? So to solve for B, I'm just going to divide both sides by the 782,000 and then do the 10th root. On your calculator, you can do that a couple of different ways. So I can do the number 10, and then if I hit math and then command 5, that allow me to like write it as a 10th root, and I can just do like 895,193 divided by 782,248. So I get that number. Or I could have just taken that division problem. This is the way that I prefer to do it. 782,248, and raise that to the 1/10th power. I like doing that because it's all on my keyboard. I don't have to go through any menus. But I get the same number either way. Now, if it's me doing this problem, I'm going to store this number as a variable. So I'm going to press this STO button. I'm going to store it as the letter B, so that if I have to do something with this later, I can take all the decimal points with me. Especially if I have a B value that's this close to 1. It's going to be a little bit sensitive to rounding, so I'm just going to take all the decimals with me, so it's going to maintain all the accuracy I can. Joe? So I just used the STO button to get the arrow, and then I did alpha, and then there's the green letters up above the commands. Yeah. So I just did alpha and then the at to get the letter B and just pressed enter. So now if I recall that letter B, that number is stored inside of it. So it allows me to take that number and use it some other time without having to like try to track back through and like grab it from the command line or something. Okay, so what I have now is everything I need. I have y equals, and I have my A, and then I have my B. I'm just going to write it this way for now. On my calculator, I've stored that value for later. So that's my equation. What I'm going to do then now is I'm going to set it equal to 1 million. And solve for x. Now, if you remember back to last year, what could you use to solve this algebraically? What would you need to use to solve this equation algebraically?
Log.
I would need to use a logarithm. Have we talked about logarithms yet? No. If you feel comfortable using one, though, you're welcome to solve this algebraically. I'm going to show you how to do it with just using your calculator and doing it graphically for the time being. We will talk about how to solve this stuff with logs in a couple of sections when we talk about logs again. But for right now, we're just going to do it algebraically, or graphically with our calculator. So what I'm going to do to solve this is I'm just going to graph the left-hand side and right-hand side. So 782,248 times. Then I'm going to call that variable b that I made before to the x. And then I'm going to do 1 million as the other side. So that's going to be graph the left-hand side and the right-hand side and look for the intersection. If I want the intersection, though, I'm going to have to set a window for this. So if I look at this, we started at about 800,000. 10 years later, we got to about 900,000. I'd expect 10 years later, we'll probably top up over 1 million. But I'm going to do a little bit more than that. So I'm going to do 0 to 30. Now, I know that what I did was like linearize this, and an exponential is going to grow faster than a linear. So like it certainly should happen within 20 years. All I'm doing is trying to get like a really rough estimate to find an upper bound. The exponential will always be faster than a linear change, but it's enough to get me like an idea of what to set that range at. And then for the y's, well, I know we're starting at 782,000, so maybe I'll just start like 700,000 as my minimum. And we have to go up to at least 1 million, so I want to set my y max something bigger than that. So I did 1.5 million. And that ought to do. So here's the picture. So here comes my population curve. Looks pretty straight because that b value is very close to 1. There's the 1 million line. I'm just looking for the intersection, so I'll press second and trace. Pick the intersect command. And since there's only 2 curves, none of these questions really matter to me. I'm just going to press enter 3 times. And it'll spit out 18.21-ish. And then that, remember our unit though is years after 1990, right? But that's not what the question asked, right? It says in what year will the population reach 1 million? So I would say between 2008 and 2009. Does everybody feel okay there? Okay. So one of the problems here with exponential functions is say, well, what if I wanted to do like y1 of 1,000, right? That would be the population of the city in the year 2990. Look at what that is. 5 points, or 5, and then a 6, and then 10 zeros after that. Is that 560 trillion or 560 billion? I don't think that the Earth could handle 560 billion people on it. Right? Everybody agree? So this is one of the bad things about these exponential functions is that they're probably not a great model for a population given like unlimited amount of time, right? What's going to happen if you're trying to grow a city? Eventually you run out of space to expand to, so you have to start growing vertically. Well, that would also mean you have to like change all your infrastructure, so like your roads need to change if you're going to build up, and like your water system and your electricity, and all that stuff needs to come in. And then you have to have enough food to support that kind of population, and like, you know, like medical care for the increased disease when people live in closer. It becomes like there's a whole bunch of limiting factors that kind of stack on top of that to tamp your population down after it gets big enough, right? So ideally what we want to describe a function or describe a population function is something when the population is low, it grows like an exponential, but as it starts getting high, it kind of levels off, right? So we do have a kind of function that does that. It's called a logistic function. And this is not something that you talk about in your Algebra 2 class, right? We will talk about these in AP Calculus some more. So if you're taking that, this is a good one. So a logistic function is of the form f of x equals c over 1 plus a times b to the x, or f of x equals c over 1 plus a times e to the negative kx. So in both of these cases, a and c are required to be positive values. And we call this logistic growth when b is between 0 and 1. And we call this decay when the b is then greater than 1. And we call this growth if k is greater than 0 and decay when k is less than 0. So one of the key features of a logistic function is we actually have two horizontal asymptotes. One of them is going to be y equals 0, and the other is going to be y equals c. We often call c the limit to growth or the carrying capacity. So that would be like, what's the maximum population that like an area could obtain based on the constraints involved, like how much space and food and resources and all that kind of stuff. So just as a quick little example, getting used to the picking the pieces out of an equation, a logistic equation. So let's take a look here. So if I look at this guy, is this going to be logistic growth or decay? Growth. It's the opposite of what you'd expect because it's in the denominator, right? Okay. If I wanted to graph this, we could do that. So I'm just going to clear the stuff out in my y equals. And here I'm definitely going to use that fraction command. So I'm going to do alpha y equals and then pick that first option. So that's going to be 10 over 1 plus 3 times 0.6 to the x. I'll graph that from, let's go negative 10 to 10. And then for the y's, I know the asymptotes are at y equals 0 and y equals 10. So we'll use that as our min and max for the y's. So there's my logistic curve. You see how it looks like a letter S? Sometimes we call these S curves. So there's my asymptotes. That was real easy. It also says find the y-intercept. Remember, the y-intercept is where the x-coordinate is 0. So if I do that, 0.06 to the 0 is 1. 1 times 3 is 3. 3 plus 1 is 4. So that becomes just 10 over 4 or 5 over 2. Or we can say just the point 0, 2.5 is the y-intercept. Jump on. Certainly. You guys feel okay there? Right? No big deal. We've seen what it looks like. Again, if we go back and look, when the population is small, grows like an exponential, and then it gets, as population starts getting big, it levels off, which is exactly what we'd want like a population curve to look like. Nolan?
Would it be like an asymptote at the top there?
Yeah. In fact, there's two asymptotes for these. One is at 0 and the other is at y equals c. So y equals 10 is our other asymptote right there at the top.
C is just the numerator?
Yes. Yes. 100%. All right. Let's do one story problem example where we give you one of these logistics to deal with. And then we are Audi 3000. So it says the population of a city can be modeled using a logistic growth equation P of t equals yada, 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 where P is the population t years after 1990. At the beginning of what year will the population be 1 million? So what we really want to do is we just want to solve P of t equal to 1 million, right? Everybody's cool? Okay. Well, that's easy enough. I'll just go to my calculator. I'm going to plug in my function. 1425397. and then 1 plus 21.783, and then we have e to the negative 0.04982 times t, and then that'll go away, and I'll just put 1 million there. Okay, so that's that. We'll set a window here. So obviously t is time, so 0 to start. Years after 1950, I don't know, but I don't know, I just pick like 100. That feels like a fair guess. We can always make it bigger if we have to, but I guess within 100 years, we should get there. The population, or the y is the population, so the horizontal asymptotes are 0 and 1,425,000, yada, yada, yada. Instead of doing that exactly, I'm just going to do like 1.5 million because it feels like it's less annoying to type into my calculator. Okay, we'll hit graph. So here's my population curve. There's the 1 million line. I'm just looking for the intersection. So second trace, intersect command, enter, enter, enter. And I get that t is 79,001,651 or something. And this is years after 1950. So what would my answer be? It says, at the beginning of what year does the city have 1 million people? That's actually going to be incorrect. What should the answer actually be? Well, it says the beginning of what year? So we had to actually round that up to 80. Because if I round down, we'll be less than 1 million, even though everything in our instinct tells us, oh, I should round that to 79. The word beginning is telling us round up no matter what. So the real answer is 2030. Ha ha, I tricked you. I wasn't trying to trick you though. That's why I'm showing it to you, so I can't fool you more than once. That's it for me for today. At this point, you have enough to do 1 through 16. That's all I'm going to ask you to do this week. Next time, we're going to have the test and all that. Joe, what's up? Hi. God bless you.
Bless you.
Can I see why the one to the power thing? No, actually, I want to see.
All right, we can talk about that. I'm going to stop the recording to do that, though, because